Earth's crust supplies the raw materials that shape almost every object humans use daily. When you pause to consider the origin of the things around you, it becomes clear that the ground beneath our feet is not simply a platform we walk upon, but rather a vast storehouse of materials that have been cycling through transformation for billions of years. Rocks formed in ancient seas, volcanoes, and mountain belts are broken down and reused in modern life, connecting us to epochs so distant that the continents themselves were arranged differently, the atmosphere held different proportions of gases, and life on the surface took forms we can barely imagine. The coffee mug on your desk, the walls surrounding you as you rest, the roadways you travel, all of these contain fragments of deep time, pieces of a planet that has been reshaping itself since long before any human walked upon it. Sedimentary rocks like limestone and sandstone record environments that existed millions of years ago. Limestone, in particular, often originates from the accumulation of countless shells and skeletal fragments of marine organisms that lived in warm, shallow seas. These creatures extracted calcium carbonate from seawater to build their protective structures, and when they died, their remains drifted down to the seafloor, layer upon layer, compacting over millennia into solid stone. Sandstone tells a different story, one of ancient beaches, rivers, and deserts where grains of quartz and other resistant minerals were carried by wind and water, sorted by size and density, and eventually cemented together by mineral-rich fluids percolating through the spaces between grains. Each layer in these rocks is like a page in a book, recording the conditions of deposition, the climate of the time, even the direction of ancient currents and winds. Igneous rocks such as basalt and granite form from molten magma and lava deep within the earth. Basalt, dark and fine-grained, crystallizes relatively quickly from lava that reaches the surface during volcanic eruptions or oozes out along mid-ocean ridges where tectonic plates pull apart. The rapid cooling doesn't give crystals much time to grow, resulting in a rock with small mineral grains that lock together tightly. Granite, by contrast, forms deep underground where magma cools slowly over thousands or even millions of years, allowing large, interlocking crystals of quartz, feldspar, and mica to develop. This slow crystallization gives granite its characteristic speckled appearance and its considerable strength. When you see granite countertops or building facades, you're looking at stone that once existed as a molten body miles below the surface, slowly solidifying in the darkness of the Earth's interior. Metamorphic rocks like marble and slate are transformed by heat and pressure inside the crust. Marble begins as limestone, but when buried deep or caught in the grip of tectonic forces during mountain building, the heat and pressure cause the calcite crystals to recrystallize, growing larger and interlocking more tightly, erasing the fossils and sedimentary structures that may have once existed. The result is a rock with a uniform crystalline texture that can be polished to a high luster, prized for sculpture and architecture for millennia. Slate forms from shale, a rock made of clay minerals and fine sediment. Under directed pressure, usually during the collision of tectonic plates, the clay minerals align perpendicular to the stress, creating planes of weakness that allow the rock to split into thin, flat sheets. This property makes slate ideal for roofing tiles and writing surfaces, and it represents a rock that has been fundamentally reorganized at the molecular level by the forces operating within Earth's crust. The rock cycle continuously reshapes minerals through erosion, burial, melting, and recrystallization. This cycle has no true beginning or end, but operates as a set of interconnected pathways by which rocks transform from one type to another. Surface rocks weather under the assault of rain, frost, wind, and chemical reactions with the atmosphere. The resulting fragments wash into streams, are carried to the sea, and accumulate as sediment. Over time, The weight of overlying material compresses these sediments into sedimentary rock. If buried deeply enough, rising temperatures and pressures transform them into metamorphic rock. If conditions become extreme enough, the rock melts entirely, becoming magma that may eventually cool into igneous rock. And once that igneous rock reaches the surface through uplift and erosion, it too begins to weather, and the cycle continues. It's a process that operates on timescales almost incomprehensible to human experience, yet it's the fundamental mechanism by which the solid Earth renews itself. Many everyday materials begin as ore minerals concentrated by geological processes. An ore is simply a rock or mineral deposit from which a valuable substance, usually a metal, can be extracted economically. These concentrations don't happen randomly. Geological processes such as magmatic differentiation, where heavy minerals settle out of cooling magma, or hydrothermal circulation, where hot fluids dissolve and then redeposit minerals in cracks and cavities, create zones where valuable minerals accumulate in much higher concentrations than their average abundance in Earth's crust. Weathering can also concentrate ores, as when rainwater dissolves away common minerals but leaves behind resistant ones like gold or aluminum-rich bauxite. These geological quirks, operating over millions of years, create the deposits that humans have sought throughout history. Mining extracts these rocks and minerals from Earth's surface and subsurface. The methods vary enormously depending on the depth, size, and nature of the deposit. Surface mining, including open pit and strip mining, removes overlying material to access deposits near the surface. Underground mining follows ore bodies deep into the crust through shafts and tunnels, a more dangerous and expensive proposition but necessary when valuable minerals lie far below. Quarrying extracts dimension stone and bulk materials like limestone or granite from large, relatively pure deposits. Each method represents a direct intervention in the rock cycle, accelerating processes that would otherwise take geological timescales and bringing buried materials to the surface in months or years instead of millions of years. Processing and refining turn raw rock into usable materials. Ore extracted from the ground rarely consists of pure metal or mineral. Instead, it's mixed with worthless rock called gangue, and the valuable component must be separated and concentrated. This might involve crushing the ore and using differences in density, magnetism, or chemical properties to separate valuable minerals from waste. Metals are often extracted through smelting, where heat and chemical reactions separate the metal from oxygen and other elements it's bonded with. The resulting refined materials, purified and processed, bear little resemblance to the rocks they came from, yet they remain fundamentally products of geological processes rearranged and concentrated by human industry. Modern society is built on this constant interaction between geology and human needs. Every generation has relied on the materials Earth provides, from the flint tools of the Stone Age to the silicon chips of the Information Age. The difference now is one of scale and sophistication. We extract vastly more material than our ancestors did, process it more completely, and use it in more complex ways. Yet the fundamental relationship remains unchanged. We are, in a very real sense, creatures of the Earth's crust, dependent on its materials for shelter, tools, and infrastructure, participants in the rock cycle through our mining, refining, and eventually disposing of the materials we extract. The walls in many homes contain gypsum, a mineral used to make drywall and plaster. Gypsum is calcium sulfate dihydrate, a soft mineral that forms in evaporating seas and salt lakes and around hot springs and volcanic vents. When seawater evaporates in enclosed basins, Dissolved minerals precipitate out in a predictable sequence, with gypsum forming after more soluble salts have crystallized but before the least soluble ones. Vast gypsum deposits exist in sedimentary sequences around the world, records of ancient seas that dried up under hot climates. When heated, gypsum loses most of its water, forming plaster of Paris, a fine powder that, when mixed with water, recrystallizes into a solid mass. This property makes it ideal for casting, molding, and creating the flat panels of drywall that form the interior walls of most modern buildings. Plaster ceiling roses and decorative moldings are often made from gypsum, a soft sulfate mineral. The tradition of using plaster for architectural ornamentation stretches back thousands of years. Its workability when wet, its ability to capture fine detail, and its relative hardness when set make it perfect for creating the decorative elements that add character to buildings. The plaster can be cast in molds or worked by hand, allowing craftspeople to create everything from simple cornices to elaborate ceiling medallions. Each of these decorative elements represents gypsum that once lay in horizontal beds of sedimentary rock, deposited in some ancient evaporating sea, later quarried, heated, rehydrated, and shaped by human hands into forms that have nothing to do with its geological origin yet remain fundamentally geological in substance. Ceramic tiles and toilets are made from clay-rich rocks that have been mined, processed, and fired. Clay minerals form primarily through the chemical weathering of feldspar-rich rocks like granite. As rainwater, slightly acidic from dissolved carbon dioxide and organic acids, percolates through soil and rock, it breaks down feldspars, dissolving some elements and rearranging others into new mineral structures. The resulting clay minerals are extremely fine-grained, platy in shape, and have a remarkable property. When mixed with water, they become plastic and moldable, yet when heated to high temperatures, they harden permanently into a dense, water-resistant material. This transformation, from soft mud to hard ceramic, involves the breakdown of the clay mineral structure and the formation of new, more stable minerals and glass-like phases. Feldspar and clays help make porcelain bathtubs and sinks strong, white, and glossy. Porcelain is a high-fired ceramic made from a mixture of clay, feldspar, and quartz. The feldspar in porcelain serves as a flux, melting at relatively low temperatures and helping to bind the other materials together. As the porcelain is heated to temperatures around 1200 degrees Celsius, the feldspar partially melts, filling the spaces between particles and creating a dense, glassy material that is impermeable to water and highly resistant to chemical attack. The whiteness of porcelain comes from the purity of the raw materials, particularly the use of kaolin, a white clay, and the absence of iron and other elements that would impart color. The glossy surface results from the glass-like phases that form during firing, creating a smooth finish that is both beautiful and functional. Fireplace bricks and fireclay linings come from heat-resistant clay minerals such as kaolinite. Not all clays can withstand the intense heat of a fireplace, furnace, or kiln. Common clays contain minerals and impurities that melt or decompose at relatively low temperatures. Fireclay, however, is composed primarily of kaolinite and has a very high melting point, allowing it to maintain its structure at temperatures that would reduce ordinary clay to a molten puddle. These refractory properties have been recognized and utilized for thousands of years, wherever humans have needed to contain and control fire. The firebricks that line a fireplace or wood stove are carefully formulated from these special clays, shaped, and fired to create a material that can endure repeated heating and cooling without cracking or losing strength. Chimney bricks in many homes are made from fired clays that originated as weathered feldspar-rich rocks. The transformation from rock to clay to brick represents a journey through multiple stages of the rock cycle. First, the original igneous or metamorphic rock, rich in feldspar, undergoes chemical weathering, breaking down into clay minerals. These clays are transported by water, deposited in layers, and later extracted for brick making. Mixed with water and sometimes sand or other materials to adjust their properties, the clay is shaped into bricks and dried. Then comes the firing, in kilns heated to temperatures around 1000 degrees Celsius. During firing, the clay minerals break down, water is driven off, and new mineral phases form, creating a material that is much harder and more durable than the soft clay it began as. The red color typical of many bricks comes from iron oxides in the clay, oxidizing during firing to produce the characteristic warm tones. Cement for concrete is produced by heating limestone and clay, so sidewalks and foundations are altered sedimentary rock. The manufacture of cement involves taking these two types of sedimentary material, crushing them together, and heating them in a kiln to temperatures around 1450 degrees Celsius. At these extreme temperatures, the limestone decomposes, releasing carbon dioxide, and the calcium oxide that remains reacts with silica, alumina, and iron oxide from the clay to form new compounds called calcium silicates and aluminates. These compounds, when ground into a fine powder, form cement. When cement is mixed with water, it undergoes a complex series of chemical reactions that cause it to harden into a solid, binding together whatever sand and gravel are mixed with it. Concrete, then, is not just sedimentary rock repurposed, but sedimentary rock that has been chemically transformed and recombined with other rock fragments to create an entirely new material. Concrete bridges and tunnels combine gravel, sand, and cement, all direct products of the rock cycle. Gravel and sand are simply fragments of rock, broken down by weathering and erosion and sorted by size through the action of water or wind. They might include quartz grains from weathered granite, limestone pebbles from eroded reefs, or volcanic fragments from weathered basalt. The diversity of rock types in typical concrete aggregate reflects the geological diversity of the region where it's sourced. When these fragments are bound together with cement, the result is a composite material that mimics, in some ways, a sedimentary rock like conglomerate or sandstone, but one that has been engineered for specific properties of strength, durability, and workability. Every concrete structure represents tons of Earth's crust, extracted, processed, mixed, and formed into shapes that serve human purposes. Road base and concrete aggregate often use crushed limestone or dolomite formed in ancient seas. These carbonate rocks, composed mainly of calcite or dolomite minerals, represent the accumulated remains of billions upon billions of marine organisms, along with chemical precipitates from seawater. They form in warm, shallow marine environments, often in tropical or subtropical latitudes where conditions favor the precipitation of calcium carbonate. Over geological time, these deposits are buried, lithified, uplifted, and exposed at the surface, where humans quarry them for construction purposes. The limestone in a roadbed might have formed as a coral reef 300 million years ago, when the area was beneath a warm sea teeming with life forms that would now seem alien to us. It was later compressed into stone, uplifted during mountain building, weathered, and finally quarried to provide a stable base for modern transportation routes. Flood defenses and riprap use hard rocks like granite or basalt to resist erosion. These igneous rocks, born from molten magma and crystallized into interlocking mineral grains, possess considerable strength and resistance to physical and chemical weathering. Granite, with its large crystals of quartz, feldspar, and mica, is particularly resistant because quartz is one of the most chemically stable minerals at Earth's surface. Basalt, though finer-grained, is also durable and widely available, often quarried from ancient lava flows or volcanic rock formations. When large blocks of these rocks are placed along shorelines, riverbanks, or the bases of structures, they absorb the energy of moving water, protecting softer materials and soils from being washed away. In essence, humans are using the products of volcanic and plutonic processes, rocks that formed under extreme conditions deep within the Earth, to protect against the erosive power of water at the surface, completing a kind of geological symmetry. Granite countertops are polished slabs of intrusive igneous rock rich in quartz, feldspar, and mica. When you run your hand across a granite countertop, you're touching a surface that formed miles beneath the Earth's surface, where temperatures were high enough to melt rock into magma but not so high that the magma erupted violently to the surface. Instead, this magma cooled slowly over perhaps hundreds of thousands of years, allowing the minerals dissolved within it to crystallize gradually into the distinctive interlocking grains that give granite its strength and visual appeal. The quartz appears as glassy, often grayish crystals. The feldspar provides white, pink, or salmon-colored rectangular crystals, and the mica forms small flakes of black biotite or silvery muscovite that catch the light. Each slab of granite is unique, its particular pattern of colors and crystals determined by the exact chemical composition of the original magma and the specific conditions under which it cooled. The process of creating a granite countertop involves quarrying massive blocks from the earth, slicing them into slabs with diamond-studded saws, and polishing the surface with progressively finer abrasives until it achieves a mirror-like finish that reveals the full beauty of the stone. Marble flooring and statues come from metamorphosed limestone or dolostone. The marble beneath your feet or carved into sculpture began its existence in a completely different form, as layers of lime mud and shell fragments accumulating on an ancient seafloor. Over millions of years, these sediments were buried, compressed, and then subjected to the intense heat and pressure of metamorphism, typically during the collision of tectonic plates and the formation of mountain ranges. During this transformation, the original sedimentary structures dissolved away as the calcite or dolomite crystals recrystallized into a new, interlocking mosaic of grains. This recrystallization gives marble its characteristic sugary texture and allows it to take a high polish. The pure white marble prized by sculptors forms from exceptionally pure limestone, while the veined and colored varieties that make marble floors so striking result from impurities, streaks of clay minerals, iron oxides, or organic matter that were present in the original limestone and became concentrated along certain planes during metamorphism. Michelangelo sought the purest white marble from Carrara in Italy, stone that had been metamorphosed during the Alpine orogeny, selecting blocks with a clarity and fine grain that would allow him to capture the subtlest details of human anatomy in stone. Roofing slate is a metamorphic rock whose aligned minerals allow it to split into flat sheets. The journey from mud to slate is a story of pressure and alignment. Slate begins as shale, a rock formed from the compaction of clay-rich mud deposited in quiet water environments like lake bottoms or deep ocean basins. When this shale is caught up in mountain building events, it experiences directed pressure as tectonic plates collide and compress the rock. This pressure causes the platy-clay minerals within the shale to rotate and align perpendicular to the direction of maximum stress, like a deck of cards being compressed from the sides until all the cards lie parallel. This alignment creates what geologists call foliation, a fabric within the rock that consists of parallel planes of weakness. A skilled slate splitter can tap along these planes with specialized tools, causing the rock to separate into thin, flat sheets perfect for roofing tiles. The best roofing slate is fine-grained, uniform in thickness, and durable enough to last for a century or more on a roof, shedding water and resisting the weathering that would quickly destroy lesser materials. The color of slate depends on its mineral content, with black slate owing its color to organic carbon, green slate containing chlorite, and purple or red slate bearing iron oxides. Garden stepping stones and pavers are often sandstone or concrete incorporating sand and gravel. Sandstone used for this purpose is typically quarried from relatively young, well-cemented formations where the original sand grains have been bound together by mineral cement, usually silica, calcite, or iron oxides. The porosity and permeability of sandstone vary considerably depending on how well cemented it is, with tighter sandstones being more suitable for use in wet environments where freeze-thaw cycles might damage more porous varieties. The sand grains themselves are usually quartz, one of the most resistant minerals to weathering, which means that a sandstone pathway contains grains that may have survived multiple cycles through the rock cycle, perhaps eroded from ancient mountains, deposited in an even more ancient river, lithified into sandstone, then uplifted and weathered again, deposited in a new environment, and finally cemented into the stone that now forms your garden path. Concrete pavers, by contrast, are recently manufactured sedimentary rocks, if you will, where sand and gravel are bound together with cement in molds, creating uniform shapes that can be arranged in patterns. The aggregate in these pavers might include anything from river-rounded pebbles to angular crushed stone, each piece carrying its own geological history. Decorative garden gravel can be quartz, marble, basalt, or other crushed rock chosen for durability. The selection of gravel for landscaping is not just aesthetic but also practical, as different rock types weather at different rates and behave differently under various environmental conditions. Quartz gravel, often appearing as white or pink pebbles, is extremely durable, as quartz is nearly inert at Earth's surface and resists both chemical and physical weathering. Marble gravel provides a bright white appearance but is more susceptible to dissolution by acidic rainwater, which can slowly etch and dull its surface over years of exposure. Basalt gravel, dark and dense, provides excellent contrast in landscaping and is highly durable, though it can retain heat on sunny days. River rock, rounded by the constant tumbling action of flowing water, represent stones that have already survived significant weathering and transport, pre-sorted by nature for durability. Each type of decorative stone in a garden bed represents a different geological environment and process, brought together by human choice to create patterns and textures that have no natural equivalent. Many city statues and historic buildings are carved from limestone or marble. Limestone has been a favored building stone throughout history because it is relatively soft when freshly quarried, making it easy to carve and shape, yet it hardens somewhat on exposure to air as moisture evaporates from the pores. This property allowed ancient and medieval stonemasons to create intricate architectural details and sculptures without the difficulties associated with working harder stones. However, limestone's composition makes it vulnerable to acid rain, a particular problem in industrial and post-industrial cities where sulfur dioxide and nitrogen oxides in the atmosphere dissolve in rainwater to form weak acids. These acids slowly dissolve the calcium carbonate of limestone, causing surface details to blur and erode over time, turning crisp carvings into softened forms. Marble, being metamorphosed limestone with larger, more tightly interlocking crystals, is somewhat more resistant but still vulnerable to acid attack. The preservation of historic limestone and marble buildings and monuments has become an ongoing challenge, requiring careful cleaning, consolidation, and sometimes protective coatings to slow the inevitable weathering that affects all rock exposed to the elements. Soapstone, rich in talc, is carved into countertops, stoves, and art pieces. Soapstone is a metamorphic rock composed primarily of talc, along with varying amounts of chlorite, pyroxene, and amphibole minerals. Talc is the softest mineral on the Mohs hardness scale, rating just 1, which means it can be scratched by a fingernail. This extraordinary softness comes from its crystal structure, consisting of sheets of silicon, oxygen, magnesium, and hydrogen bonded together strongly within each sheet but very weakly between sheets, allowing them to slide past each other easily. This structure gives talc, and therefore soapstone, a greasy or soapy feel, which is where the rock's name originates. Despite its softness, soapstone is remarkably dense and has an exceptional ability to absorb and retain heat, making it ideal for wood stove linings and surrounds, as well as griddles and cooking surfaces that can be heated directly. The stone's ease of carving has made it a favorite for sculpture and decorative objects throughout history, from ancient seals and amulets to modern countertops that can be worked with ordinary woodworking tools. Soapstone typically forms in metamorphic environments where magnesium-rich rocks undergo alteration by heated fluids, a process that replaces the original minerals with talc and associated minerals. Pumice stones used for exfoliating feet are frothy volcanic rock. Pumice forms during explosive volcanic eruptions when lava containing dissolved gases is ejected into the air and cools rapidly while the gases are still expanding and escaping. The result is a rock so filled with tiny bubbles that it often has a lower density than water and can float, at least until the pores become waterlogged. The pumice you use to smooth rough skin might have formed in an eruption thousands of miles away, cooled in seconds from molten lava to solid rock, been broken into fragments by the explosive force of the eruption or by subsequent weathering, transported by rivers to the sea, and eventually collected, processed, and sold for personal care use. The abrasive quality of pumice comes from its texture, the rough walls of countless tiny vesicles, the bubble-shaped cavities left by escaping gas, which act like microscopic files when rubbed against skin or other surfaces. The same properties that make pumice useful for smoothing feet have made it valuable for other purposes throughout history, from abrading and polishing surfaces to lightweight aggregate in concrete, where its low density reduces the weight of the final structure without substantially compromising strength. Landscaping lava rock is usually scoria formed from gas-rich lava. Scoria is similar to pumice in origin, both being vesicular volcanic rocks, but scoria typically has larger vesicles, a darker color, and a higher density that prevents it from floating. It forms from basaltic lava, which is darker and richer in iron and magnesium than the rhyolitic lava that typically produces pumice. As the lava erupts and solidifies, gases including water vapor, carbon dioxide, and sulfur dioxide expand and create bubbles, but the lava is viscous enough that the bubbles are trapped as the rock solidifies rather than escaping completely. The resulting rock is full of holes, giving it a distinctive appearance and much lower density than solid basalt. The dark red, brown, or black color comes from iron oxides within the basalt, oxidized as the rock cooled and was exposed to air. In landscaping, scoria serves multiple purposes beyond decoration. Its porous structure allows water and air to pass through, improving drainage in planting beds, and its dark color provides excellent contrast against plants and other landscape elements. The rock's rough, vesicular texture also provides grip on slopes and pathways, reducing the risk of slipping. Roofing granules on asphalt shingles are crushed, colored rock. If you examine an asphalt shingle closely, you'll see that its surface is covered with small, hard particles embedded in the asphalt coating. These granules serve several critical functions beyond simply giving the shingle its color. They protect the underlying asphalt from ultraviolet radiation from the sun, which would otherwise cause the asphalt to degrade and become brittle. They provide fire resistance, create a textured surface that helps rainwater disperse rather than run off in sheets, and contribute to the shingle's reflective properties, affecting how much solar heat the roof absorbs. The granules are typically made from crushed basalt, although other hard rocks may be used, and they are coated with ceramic pigments to provide the desired color and UV resistance. The process of manufacturing these granules involves mining the rock, crushing it to a specific size range, applying the ceramic coating in high-temperature kilns, and then sorting the granules by size before they are applied to the shingles. Each shingle contains thousands of these tiny rock fragments, making a typical roof a mosaic of crushed volcanic stone, bound with petroleum products derived from ancient organic matter, protecting the building beneath from rain, sun, and weather. Glass windows are made from sand rich in quartz. The transformation of sand into glass is one of humanity's most ancient and important technological achievements. Quartz sand, essentially tiny grains of silicon dioxide, melts at around 1700 degrees Celsius. When this molten silica cools rapidly without crystallizing, it forms glass, an amorphous solid where the atoms are frozen in a disordered arrangement rather than the regular crystalline structure of quartz. Pure silica glass has a very high melting point and is difficult to work with, so glassmakers add other materials to lower the melting point and modify the properties of the glass. Soda ash, derived from trona or manufactured from salt, acts as a flux, lowering the melting point to around 1000 degrees Celsius. Lime, from limestone, is added to improve the chemical durability of the glass and prevent it from dissolving in water over time. The resulting soda-lime glass is what forms most windows and glass containers, a material that is transparent to visible light, impermeable to wind and water, and infinitely recyclable, melting down again and again to form new glass without any degradation in quality. Every window you look through represents sand grains that have undergone this transformation, melted from their crystalline quartz form into an amorphous state and then shaped while still hot into flat sheets. Mirrors rely on flat glass made from quartz-rich sand backed with metals like silver. A mirror is simply a piece of glass with a reflective coating, but creating a truly flat, uniform surface requires considerable precision. The glass must be free of distortions, bubbles, and irregularities that would warp the reflection. Modern mirrors are typically made by depositing a thin layer of metal, traditionally silver but now often aluminum, onto the back surface of the glass through chemical or vacuum deposition processes. This metal layer reflects almost all the light that reaches it, while the glass protects the metal from oxidation and damage. The flatness of the glass depends on the method of manufacture, with float glass, where molten glass is floated on a bed of molten tin, producing particularly flat, uniform sheets. The silica sand used in mirror glass must be extremely pure, with minimal iron content, as even small amounts of iron give glass a greenish tint that would affect the color accuracy of the reflection. The highest quality mirrors, such as those used in telescopes, require glass made from exceptionally pure silica, sometimes fused quartz, polished to within fractions of a wavelength of light to create surfaces of extraordinary precision. Vehicle window glass uses silica sand plus trona and feldspar. Automotive glass must meet different requirements than ordinary window glass, particularly the windshield, which must be strong enough to resist impacts, yet break in a way that minimizes injury if it does fail. Windshields are made of laminated glass, 2 layers of glass with a plastic interlayer, typically polyvinyl butyral, that holds the fragments together if the glass breaks. The side and rear windows are usually tempered glass, which is heat-treated to create internal stresses that make the glass stronger and cause it to break into small, relatively harmless pieces rather than large, sharp shards. The base glass is still soda-lime glass made from silica sand, but the addition of trona, a natural sodium carbonate mineral mined from ancient lake beds, provides the sodium oxide flux that lowers the melting point. Feldspar contributes alumina, which improves the glass's resistance to weathering and thermal shock. The result is a material that can withstand the temperature extremes, vibrations, and mechanical stresses of automotive use while remaining transparent and relatively safe if damaged. The minerals in your car's windows come from mines and quarries scattered across the globe, each contributing specific chemical elements necessary to create glass with the desired properties. Light bulbs contain glass from silica sand and tungsten filaments from or minerals. The glass envelope of an incandescent light bulb must be clear, able to withstand high temperatures, and thin enough to allow efficient heat dissipation, yet strong enough not to break under handling and thermal stress. The silica sand used for light bulb glass is melted and formed into bulbs through automated processes that produce millions of identical shapes. Inside the bulb, in traditional incandescent designs, is a coiled tungsten filament. Tungsten is chosen because it has the highest melting point of any metal, 3400 degrees Celsius, allowing the filament to be heated white-hot without melting. Tungsten is extracted from or minerals like wolframite and scheelite, minerals that typically form in high-temperature environments associated with granite intrusions or metamorphic rocks. The concentration of tungsten in these ores is usually quite low, requiring extensive mining and processing to extract the metal. The filament in a light bulb is drawn from tungsten wire so fine that it's almost invisible to the naked eye, coiled to increase its length and therefore its resistance, which causes it to heat up when electric current flows through it. The combination of geological materials, silica sand transformed into glass and tungsten extracted from ore and drawn into wire, allows the conversion of electrical energy into light. Road markings use tiny glass beads made from silica sand for reflectivity. When you drive at night and see the painted lines on the road glowing in your headlights, you're witnessing the optical properties of tiny glass spheres embedded in the paint. These glass beads, typically 1 to 2 millimeters in diameter, are made from silica sand melted and formed into perfect spheres. When light from a vehicle's headlight strikes these beads, it enters the sphere, reflects off the back surface, and returns toward the source, a phenomenon called retroreflection. This makes the road markings appear bright when viewed from the position of the light source, dramatically improving visibility at night and in poor weather conditions. The beads are applied to the fresh paint while it's still wet, sinking partially into the coating so that they remain securely attached as vehicles pass over them. Over time, as the paint wears away or the beads are dislodged by traffic, the reflectivity of the markings decreases, requiring repainting. Each kilometer of highway marking contains millions of these tiny glass beads, each one a perfect sphere of fused silica, working together to guide millions of vehicles safely through the darkness. Colored glass bottles use metal oxides from minerals like chromite and cobaltite. The natural color of glass made from typical silica sand is a slight greenish tint from iron impurities in the sand. To create other colors, glassmakers add specific metal oxides that absorb certain wavelengths of light while transmitting others. Cobalt oxide, derived from minerals like cobaltite, produces a deep blue glass, as cobalt strongly absorbs red and yellow light while transmitting blue. Chromium oxide, from chromite, can produce various colors depending on the oxidation state and the presence of other elements, including green, yellow, or pink. Iron can produce green, brown, or even black glass depending on its oxidation state and concentration. Manganese oxide can produce purple or pink colors, while copper compounds produce blue, green, or red, depending on conditions. Gold, in minute quantities, produces a rich ruby red glass, a technique that dates back centuries and requires extremely careful control of the glass chemistry and cooling process. Each colored bottle represents sand from a quarry or beach, melted with specific minerals chosen for their ability to modify the optical properties of glass, creating containers that not only hold their contents but also filter light and provide aesthetic appeal. Ceramic plates and mugs come from kaolin and other clays. Kaolin, also known as china clay, is a white clay composed primarily of the mineral kaolinite, an aluminum silicate. It forms through the intense weathering of feldspar-rich rocks, particularly granite, in warm, wet climates where chemical weathering is especially effective. The purest kaolin deposits form where the weathered material has been transported by water and redeposited, a process that sorts the particles by size and washes away soluble impurities, leaving behind the fine, white clay. This clay is the primary ingredient in porcelain and fine china, prized for its whiteness and the way it fires to a dense, translucent material. More common ceramic tableware uses earthenware or stoneware clays, which contain more impurities and fire at lower temperatures, producing pottery that is more porous and opaque but also more affordable and easier to manufacture. The transformation of clay to ceramic involves heating to temperatures where the clay minerals break down and new mineral phases form, along with some glass formation that binds the particles together. The exact temperature and atmosphere in the kiln determine the final properties of the ceramic, from its hardness and porosity to its color and translucency. Ceramic tiles and sanitary ware rely on feldspar as a flux during firing. In ceramic production, a flux is a material that melts at relatively low temperatures and helps bind the other components together. Feldspar, typically potassium feldspar or sodium feldspar, melts around 1200 degrees Celsius and forms a glassy phase that fills the spaces between clay particles and quartz grains, creating a dense, impermeable ceramic body. Without feldspar, the clay would need to be fired to much higher temperatures to achieve the same density, making production more expensive and difficult. The feldspar used in ceramics is mined from pegmatites, extremely coarse-grained igneous rocks that form from the last water-rich portions of crystallizing granitic magma. These pegmatites often contain large, pure crystals of feldspar that can be crushed and processed to provide the flux needed for ceramic production. The glassy phase formed by melting feldspar is what gives fired ceramic its water resistance and strength, creating a material that can withstand years of use, exposure to water, detergents, and temperature changes without degrading or absorbing stains and odors. Ceramic kitchen knives use zirconia derived from zircon sand. Zirconium oxide, or zirconia, when properly processed, produces a ceramic that is extraordinarily hard and maintains an extremely sharp edge. Zircon is a zirconium silicate mineral that occurs as a common accessory mineral in many igneous rocks, particularly granite, and accumulates in beach and river sands due to its high density and resistance to weathering. These zircon-rich sands are mined and processed to extract the zirconium, which is then converted to zirconium oxide. The zirconia is formed into knife blades by pressing the powder into molds and then sintering, heating to high temperatures that cause the particles to bond without fully melting. The resulting material is harder than steel, retains its edge much longer, and is completely non-reactive, so it won't rust or impart any taste to food. However, the hardness that makes zirconia excellent at holding an edge also makes it brittle, so ceramic knives can chip or break if dropped or used improperly, a reminder that hardness and toughness are different properties. The zircon in a ceramic knife blade may have crystallized from magma millions of years ago, survived weathering and transport to a beach or river, been mined and processed, and finally transformed into a cutting tool that represents some of the most advanced ceramic technology available. White cement uses specially selected limestone and kaolin to maintain brightness. Ordinary Portland cement has a gray color due to iron and manganese compounds present in the limestone and clay used in its manufacture. For applications where color matters, such as architectural concrete, terrazzo flooring, or decorative elements, white cement is preferred. Producing white cement requires sourcing limestone and clay with extremely low iron and manganese content, which is more expensive and limits the number of quarries that can supply suitable raw materials. The manufacturing process is also modified to minimize contamination and prevent the formation of colored compounds during firing. The resulting cement, when mixed with white or light-colored aggregates, produces concrete that can be left exposed or easily colored with pigments to produce vibrant hues impossible to achieve with gray cement. White cement represents a more refined use of geological materials, where the specific chemistry of the source rocks becomes critical, and small variations in mineral content that would be irrelevant for ordinary cement production become disqualifying impurities. It's a reminder that not all limestone or all clay is interchangeable, and that the geological history and composition of the raw materials fundamentally determine what can be made from them. Copper wiring comes from ores such as chalcopyrite. Chalcopyrite is a copper-iron sulfide mineral, brassy yellow in color and often mistaken for gold by inexperienced prospectors, though it's more brittle and has a greenish-black streak when scratched against and glazed porcelain. This mineral forms in a variety of geological settings, from high-temperature hydrothermal veins associated with igneous intrusions to massive sulfide deposits on the seafloor where hot, mineral-rich fluids emerge from volcanic vents. The copper in chalcopyrite is chemically bonded to iron and sulfur, and extracting it requires crushing the ore, concentrating the valuable minerals through flotation processes that exploit differences in how minerals interact with water and air bubbles, and then smelting the concentrate at high temperatures to separate the copper from the other elements. The sulfur is driven off as sulfur dioxide, which must be carefully captured and processed to prevent air pollution, while the iron forms a slag that's removed. The resulting copper is further refined through electrolysis to achieve the high purity required for electrical applications, where even small amounts of impurities can significantly reduce conductivity. Every meter of copper wire in your walls represents, or that was perhaps deposited by ancient hydrothermal systems, later exposed by erosion and uplift, mined from beneath the surface, and processed through multiple steps to extract and purify the metal. Steel relies on iron or minerals like hematite and magnetite. Iron is the most abundant element on Earth by mass, making up much of the planet's core, but in the crust it's dispersed in many minerals and rarely concentrated enough to be economically extracted. Hematite and magnetite are iron oxide minerals that form the primary ores from which iron is extracted. Hematite, red to silver-gray in color, is iron oxide, while magnetite is magnetic and black, a mixed valence iron oxide where iron exists in two different oxidation states. These minerals form through various processes, from direct precipitation from seawater in ancient oceans, creating vast banded iron formations that date back billions of years when Earth's atmosphere first became oxygen-rich, to concentration through weathering and secondary enrichment processes. The extraction of iron from these ores involves heating them with coke, a form of carbon made from coal, in a blast furnace. The carbon reduces the iron oxide to metallic iron, while also combining with oxygen to form carbon dioxide and carbon monoxide gases. The molten iron that results contains significant carbon and other impurities, and converting this pig iron to steel requires reducing the carbon content to specific levels, typically less than 2%, and adding other elements to create alloys with desired properties. Steel is not a pure substance but a family of iron-carbon alloys, each formulated for specific applications. Manganese from pyrolusite makes steel tougher. Pyrolusite is manganese dioxide, a dark gray to black mineral that forms through weathering and oxidation of manganese-bearing rocks, often accumulating in bogs and shallow marine environments where oxidizing conditions prevail. Manganese plays several roles in steelmaking, primarily acting as a deoxidizer and desulfurizer during the smelting process, and as an alloying element that increases the strength, hardness, and wear resistance of the finished steel. In high concentrations, manganese creates steels that are exceptionally tough and resistant to impact, used for heavy-duty applications like railroad tracks, crusher jaws, and earth-moving equipment. The manganese in a steel girder or a car suspension system represents minerals that were once part of ancient sedimentary sequences or weathered rock surfaces, now refined and incorporated into alloys that define modern infrastructure. Chromium from chromite enables stainless steel and leather tanning. Chromite is an iron chromium oxide mineral, black and often with a metallic luster, that forms in ultramafic igneous rocks and the metamorphic rocks derived from them. It typically crystallizes early from cooling magmas and, being dense, settles to form layers of chromite-rich rock in layered intrusions. Some of the world's largest chromite deposits formed this way billions of years ago and represent enormous concentrations of chromium accumulated through magmatic processes. Chromium metal is extracted from chromite by reduction with carbon or silicon, but much chromium is used directly as ferrochrome, an iron-chromium alloy produced by smelting chromite with coke and iron. When added to steel, chromium has a transformative effect. At concentrations above about 10.5%, chromium causes the formation of a thin, invisible oxide layer on the steel surface that is impermeable to oxygen and water, effectively passivating the steel and making it stainless. This passive layer, only a few atoms thick, forms instantly when the steel is exposed to air and repairs itself if scratched, providing the corrosion resistance that makes stainless steel essential for everything from kitchen cutlery to surgical instruments and chemical processing equipment. Tin from cassiterite is used in solder and tin plate. Cassiterite is tin oxide, typically brown or black, with a high density and hardness that cause it to concentrate in placer deposits where it has been weathered from tin-bearing veins and accumulated in streams. Historically, tin has been one of the most sought-after metals because, when alloyed with copper, it produces bronze, an alloy harder than either pure metal and far superior for tools and weapons than the pure copper available before the Bronze Age. Today, tin's primary uses are in solder, where its low melting point and ability to wet and bond to copper and other metals make it ideal for joining electronic components, and in tin plate, thin steel sheet coated with tin to prevent corrosion in food and beverage cans. Tin extraction is relatively straightforward compared to many metals, as cassiterite can be concentrated through gravity separation and then reduced with carbon at moderate temperatures. However, tin deposits are relatively rare, and the metal has been a commodity of international trade for thousands of years, with tin from Cornwall in England, the Iberian Peninsula, and Southeast Asia flowing across continents and seas to meet demand. The tin in solder holding together the components on a circuit board represents cassiterite grains that may have weathered from granite and concentrated in an ancient stream, been mined from placer deposits or hard rock veins, smelted, refined, and alloyed to create a material that melts at temperatures low enough to be safely used in electronics assembly without damaging heat-sensitive components. Gold is concentrated by hydrothermal fluids and used in electronics and jewelry. Gold is one of the rarest elements in Earth's crust, typically present at concentrations of only a few parts per billion, yet geological processes can concentrate it by factors of thousands or even millions to create economic deposits. Hydrothermal fluids, hot water circulating through fractured rock, can dissolve minute amounts of gold from the rocks they pass through and, when conditions change, such as temperature drop, pressure release, or mixing with different fluids, deposit that gold in veins and fractures. Over millions of years and through countless cycles of fluid flow, significant gold can accumulate in these structures. Gold also concentrates in placer deposits, where its high density and resistance to weathering cause it to settle and accumulate while lighter minerals are washed away. The metal's unique properties, its chemical inertness, high electrical conductivity, and malleability, make it valuable beyond its aesthetic appeal. In electronics, gold is used for plating contacts and connectors because it doesn't corrode or tarnish, ensuring reliable electrical connections. A single smartphone contains a tiny amount of gold, perhaps 50 milligrams, in its circuitry, but with billions of devices produced, electronics consume a significant fraction of gold production. The gold in a wedding ring or circuit board represents atoms that may have been concentrated from vast volumes of rock by hot fluids circulating through ancient faults, transported to the surface through erosion, perhaps concentrated again in a stream, and finally extracted, refined, and shaped into forms that have nothing to do with its geological origin yet remain fundamentally dependent on the processes of the deep earth. Rare earth elements like neodymium power magnets in electronics and motors. The rare earth elements are a group of 17 elements, including the 15 lanthanides plus scandium and yttrium, that share similar chemical properties and often occur together in nature. Despite their name, they're not particularly rare in terms of crustal abundance, but they are rarely concentrated into economically viable deposits. Neodymium, element 60, is one of the more abundant rare earths and is essential for making the strongest permanent magnets currently available. These neodymium iron-boron magnets, developed in the 1980s, generate magnetic fields far stronger than traditional ferrite or alnico magnets of the same size, enabling the miniaturization of motors and speakers and the development of more efficient generators for wind turbines. Rare earth elements are extracted from minerals like bastnasite and monazite, which form in carbonatites, unusual igneous rocks rich in carbonate minerals, and in placer deposits where the dense rare earth minerals have accumulated. Processing these ores to separate the individual rare earth elements is a complex chemical challenge because of their similar properties, requiring multiple stages of solvent extraction. Hard drives and speakers rely on rare earth magnets. The magnets in these devices are typically neodymium iron-boron permanent magnets, the same type used in motors but engineered for specific applications. In hard disk drives, tiny neodymium magnets are part of the voice coil actuator that moves the read-write heads across the disk platters with extraordinary precision, positioning them over the correct track in milliseconds. The strong magnetic field from these small magnets allows rapid, accurate movement. In speakers, neodymium magnets create the magnetic field that interacts with the voice coil, converting electrical signals to mechanical motion that moves the speaker cone and creates sound waves. The advantage of rare earth magnets in these applications is their combination of strong magnetic fields and compact size, allowing devices to be smaller and more efficient than would be possible with traditional magnets. The production of these magnets involves melting the constituent metals together, cooling rapidly to form the desired crystal structure, crushing the resulting material into powder, compacting it under pressure in a magnetic field to align the crystal structures, sintering at high temperature, and then magnetizing the finished magnet in a strong external field. The process must be carefully controlled at every stage because the magnetic properties depend critically on the crystal structure and grain size. The magnets in your devices represent rare earth elements extracted from unusual igneous rocks, combined with iron and boron under precisely controlled conditions, processed into finished magnets, and incorporated into devices where their powerful magnetic fields enable data storage and sound reproduction. Fluorescent and LED lights use europium and terbium phosphors. Phosphors are materials that absorb high-energy photons and re-emit lower-energy visible light, converting invisible ultraviolet or blue light into the full spectrum of colors we perceive as white light. In fluorescent lamps, the phosphor coating on the inside of the tube absorbs ultraviolet light generated by the mercury vapor discharge and converts it to visible light. In white LEDs, phosphors absorb some of the blue light from the LED chip and emit yellow or red light that combines with the remaining blue to produce white. Europium and terbium, rare earth elements numbered 63 and 65, are key components of efficient phosphors. Europium produces red emission, terbium produces green, and combinations of these with other rare earths and host materials produce the range of colors and spectral characteristics needed for high-quality lighting. The phosphor materials are complex oxides or other compounds where rare earth ions are dispersed in a host crystal, and when these ions absorb high-energy photons, electronic transitions within the rare earth atoms produce the characteristic narrowband emissions. The development of efficient phosphors required extensive research to find combinations of host materials and activator ions that would produce bright, stable emission with good color rendering properties. The rare earths in these phosphors come from the same mining and separation processes that produce neodymium and other rare earths, but they're formulated into different compounds and applied as thin coatings inside lamps or over LED chips. The quality of modern lighting, from the warm tones of incandescent replacement LEDs to the bright, color-accurate illumination in workspaces, depends on these carefully engineered phosphor materials that begin with rare earth elements from unusual geological deposits. Solar panels require high-purity silicon refined from quartz. Photovoltaic solar cells convert sunlight directly to electricity through the photoelectric effect, where photons striking a semiconductor material dislodge electrons, creating an electrical current. Silicon is the semiconductor of choice for most solar panels because it's abundant, has suitable electronic properties, and decades of development in the semiconductor industry have established efficient methods for purifying and processing it. The silicon in solar panels begins as quartz, silicon dioxide, which is reduced with carbon in electric arc furnaces to produce metallurgical-grade silicon. This material, about 98% pure, must be further refined to produce solar-grade silicon, typically by converting it to volatile silicon compounds that can be distilled to remove impurities, then decomposing these compounds to deposit pure silicon. The resulting material is formed into ingots, sliced into thin wafers, and processed to create the layered structure of P-type and N-type silicon that forms the photovoltaic junction. The purity requirements are extraordinary, with total impurities typically below 1 part per billion for certain elements that would compromise electrical properties. The entire chain, from quartz in a vein or beach sand to operating solar panel, represents one of the most complex and energy-intensive transformations of geological materials, yet it enables direct conversion of sunlight to electricity with no emissions or moving parts. The silicon in solar panels covering rooftops and fields represents quartz that has undergone multiple stages of reduction, purification, crystal growth, and fabrication to create materials where quantum effects at the junction between differently doped silicon layers convert photons to electrical current with efficiencies now exceeding 20%. When you drive down a road, you're traveling over layers of the Earth itself, compressed and arranged in a careful sequence that speaks to both engineering and geology. The black surface we call asphalt is really just the top layer, the visible face of a much deeper conversation between human needs and mineral resources. Beneath that dark, smooth coating lies crushed stone, sand, and gravel, materials that have been broken down from larger rock formations and sorted by size and strength. The asphalt itself is a mixture of these stone fragments, called aggregate, and a thick, black binder derived from petroleum. This binder, a complex mixture of hydrocarbons, is the remains of organic matter that lived in ancient seas, was buried, heated, and transformed over millions of years. So a road is a composite of deep time, combining rocks that may have formed in ancient volcanoes or oceans with the processed remains of ancient life. The engineering challenge is to choose the right materials and arrange them in layers that can support the weight of thousands of vehicles while resisting the wear and tear of weather and time. The subbase, the lowest layer, is often made of larger, less processed rock that provides a stable foundation. Above that, the base course uses smaller, more uniform stone to distribute the load. Finally, the surface layer provides the smooth ride and the grip needed for safety. Each layer must be carefully compacted to remove air spaces and create a solid mass. Now let's move from transportation and energy to something even more everyday and intimate. The substances we use in our kitchens and gardens, the materials that touch our food and help things grow. Table salt, that simple white crystal we sprinkle on food without thinking, is actually the mineral halite. Halite is sodium chloride, and it forms when salty water evaporates. This happens naturally in desert lakes, in coastal lagoons, in landlocked seas that are shrinking. The water evaporates and the dissolved salts crystallize out, forming layers that can be thick and extensive. Ancient salt deposits formed this way millions of years ago, and now they're mined for various purposes. When you shake salt from a shaker, you're using crystals that formed through evaporation, each tiny grain a perfect cube at the molecular level, each one tasting the same because the chemical composition is consistent. The salt we spread on icy roads in winter is also halite, the same mineral, but it's mined in bulk and not refined to food purity. Rock salt, as it's called, lowers the freezing point of water, helping to melt ice and provide better traction. This simple application of chemistry and geology helps keep our roads safe during winter months. Fireworks are chemistry in action, and the colors come from specific elements that emit characteristic wavelengths of light when heated. These elements come from minerals. Strontium compounds produce red light, and strontium is found in minerals like celestine, which is strontium sulfate. Barium compounds produce green light, and barium comes from barite. Copper compounds produce blue light. Sodium produces yellow light and comes from halite and other sodium minerals. Calcium produces orange light. When fireworks explode, heat excites electrons in these elements to higher energy levels, and when the electrons fall back down they emit light of specific colors. The brilliant displays of color in the night sky during celebrations are minerals being vaporized and emitting light, a visible demonstration of quantum mechanics and geology combined. Sandpaper uses hard minerals as abrasives to smooth surfaces. Garnet is a common abrasive mineral for sandpaper and other sanding products. Garnet is actually a group of minerals with similar structures but different chemical compositions. Almandine garnet, which is iron-rich, is particularly hard and durable. Garnet forms in metamorphic rocks under high pressure and temperature. Alumina, which is aluminum oxide, can be produced synthetically and is even harder than garnet. Silicon carbide is harder still and is produced by heating silica and carbon together. These materials are glued to paper or cloth in specific grit sizes, and the hardness and sharpness of the mineral grains determines how effectively the sandpaper removes material. From smoothing wood to preparing surfaces for painting, these mineral abrasives are essential tools. Drill bits that cut through hard materials are often tipped with industrial diamond. Diamond is the hardest natural material known, composed of carbon atoms arranged in a rigid three-dimensional structure. Natural diamonds form deep in the Earth's mantle under extreme pressure and temperature and are brought to the surface by rare volcanic eruptions. Industrial diamonds are often produced synthetically by subjecting carbon to similar extreme conditions in the laboratory. Because of their extreme hardness, diamonds can cut through any other material, making them indispensable for drilling in mining, construction, and oil and gas exploration. When you see a drill bit biting into rock or concrete, you're seeing the power of the strongest chemical bonds in nature at work. Gemstones used in jewelry each have their own geological origin story. Diamonds form in the Earth's mantle at depths of 100 miles or more, where carbon is subjected to immense pressure and heat. They're brought to the surface rapidly by volcanic eruptions that travel through the crust in narrow pipes. Rubies and sapphires are varieties of corundum, aluminum oxide, that forms in metamorphic rocks and sometimes in igneous rocks. Chromium gives rubies their red color, iron and titanium give sapphires their blue color. Emeralds are green beryl, colored by chromium and vanadium, and they form in specific geological settings where beryllium-rich fluids interact with chromium-bearing rocks. Each type of gemstone requires particular conditions of pressure, temperature, and chemical composition, conditions that only occur in certain places and at certain times in Earth's history. When you see a gemstone in jewelry, you're looking at a crystal that formed under specific circumstances, often deep underground, and that has survived the journey to the surface and the processes of mining, cutting, and setting. Quartz crystals, some of the most common and recognizable crystals, grow from silica-rich fluids that circulate through cavities and fractures in rock. Silica, which is silicon dioxide, dissolves slightly in hot water, especially water that's somewhat alkaline. As the water cools or as chemical conditions change, the silica precipitates out, forming crystals of quartz. If the cavity is large and the crystal growth is slow, large, well-formed crystals can develop. Clear quartz, amethyst, citrine, and rose quartz all form this way, with different impurities and conditions creating different colors. Geodes, those hollow rocks lined with crystals, form when silica-rich fluids fill a cavity and then slowly precipitate quartz inward from the walls. The process can take thousands or millions of years, each molecule of silica finding its place in the growing crystal lattice. The quartz crystals used in watches as timing elements, in electronics as oscillators, and in jewelry as gemstones all grew through this patient accumulation of silicon and oxygen atoms. Decorative stones used in buildings, countertops, and sculptures often reveal the geological processes that formed them. Marble is metamorphosed limestone, and it often shows swirls and bands of color from impurities in the original limestone or from deformation during metamorphism. Granite shows interlocking crystals of quartz, feldspar, and mica, frozen in place as magma slowly cooled underground. Fossils appear in some limestones and sandstones, preserved remnants of ancient organisms now visible in polished stone surfaces. Agate shows concentric bands of different colored quartz, each band representing a separate episode of precipitation from silica-rich fluids. These stones are chosen partly for their durability but also for their beauty, for the patterns and colors that reveal their history. A polished granite countertop is a window into the deep crust, showing minerals that crystallized from magma perhaps a billion years ago. Historic objects made of stone or metal preserve geological history in ways that connect human history to Earth history. Bronze artifacts from ancient civilizations contain copper and tin that were mined thousands of years ago. The sources of that metal can sometimes be traced through chemical analysis, revealing ancient trade routes and connections between cultures. Stone tools from prehistoric times show which rock types were valued for their properties, which sources were exploited, how materials moved across landscapes. The flint used for arrowheads and scrapers is a form of quartz that fractures in predictable ways, creating sharp edges. Obsidian, volcanic glass, was traded over long distances because of its superior sharpness and workability. Every historical artifact made of stone or metal is both a cultural object and a geological specimen, carrying information about the Earth as well as about human societies. Everyday life, when you pay attention, is a quiet exhibition of Earth's deep time. The salt on your table, the graphite in your pencil, the steel in your car, the concrete in your sidewalk, the glass in your windows, all of these materials have geological origins. They represent specific mineral deposits, specific formation processes, specific moments in the Earth's long history. The iron in your blood came from ancient stars that exploded billions of years ago, scattering heavy elements into space. Those elements eventually became part of the solar nebula that formed our sun and planets. The iron in the Earth's core, the iron in the ore we mine, and the iron in your hemoglobin all share this cosmic origin. We are literally made of stardust, and the materials we use every day are the products of a long and complex history of cosmic and geological evolution. Understanding this history gives us a new perspective on the world around us. It helps us appreciate the complexity and beauty of the planet we live on and the resources we depend on. It also reminds us of our responsibility to use these resources wisely and sustainably, recognizing that they are finite and that their extraction and use have significant impacts on the environment. Geology isn't just about the past, it's also about the future. By studying the Earth's history, we can better understand the processes that shape our planet today and the challenges we face in the years ahead. We can learn how to find and use new resources, how to mitigate the impacts of natural disasters, and how to protect the environment for future generations. The story of the Earth is our story, and the materials we use every day are the chapters of that story. By paying attention to these materials and their origins, we can deepen our connection to the planet and our understanding of our place in the world. The journey of a single mineral grain, from its formation deep in the earth or in the heart of a star to its place in a modern technological device, is a testament to the interconnectedness of all things and the power of human ingenuity to transform the raw materials of nature into the tools of civilization. As we look to the future, we will continue to depend on the Earth's resources, but we must also learn to live more harmoniously with the planet, recognizing that we are not separate from nature but a part of it. The materials we use, the energy we consume, and the waste we produce are all part of the Earth's cycles, and our actions have consequences that will be recorded in the geological record for millions of years to come. By understanding our geological heritage, we can make more informed choices about how we live and how we use the resources of the Earth's evolution and structure. Geology isn't just about mountains and earthquakes and the formation of continents. It's also about the coffee cup you're holding, the chair you're sitting on, the building around you, and the countless mineral-derived materials that make modern life possible. Every object is a geological specimen. Every day is a lesson in earth science, if you know how to look, if you remember to pay attention. The Earth provides everything we use, everything we touch, everything we build. We are not separate from the planet but deeply embedded in its systems, dependent on its resources, shaped by its constraints. The minerals we extract and use will eventually return to geological cycles, perhaps to be concentrated again in some future or deposit, perhaps to become part of some future civilization's technology. The atoms are conserved even as their arrangement changes. The elements persist even as they move through different forms. And in this great cycling of materials, this endless transformation and reorganization, we find both our place in nature and our connection to deep time, to the long history of the Earth and the even longer history of the cosmos. When you go about your day tomorrow, perhaps you'll see the objects around you a little differently. Perhaps you'll recognize the geological heritage in everything you touch, and perhaps that recognition will bring a quiet sense of wonder at how intimately we're woven into the fabric of the planet.